Greetings, everyone. My name is Russ Newburg, and I am the Director of Operations with Holland in charge of RMSS, our Rail Measurement Systems and Services Division here at Holland. Today, I'm going to walk through a short presentation where we're going to talk about our Holland TrackStar track testing and take a look at the fastening system inspection part of what we do and how GRMS plays a role in geometry analysis. This presentation was also put together with the assistance of our Director of Product Development, Sabri, Cakdi. Before we get into GRMS, I wanted to take a moment to introduce Holland and who we are, along with some of what we do in the industry. RMSS is part of our maintenance away team and global rail services group that represents some of our 85-year history to the market. We are a market leader in both flash butt arc welding technologies, fixed plant welding, and mobile welding environments that cater to railroads and transits throughout North America and Australia. To highlight a few things that Holland does besides flash butt arc welding, we have cutting edge laser frog welding technology that we developed and introduced into the market about 3 years ago. Along with our Holland turnkey construction services, we have our proprietary Argus measurement system and services suite, as well as the ability to perform more of the traditional thermite welding. So we are a full scale operating group. Let's discuss what GRMS inspection is and why it's important to have the GRMS analysis of track as it's related to the fastening and crosstie evaluation. We're going to go over a couple things in this short presentation today, specifically what is GRMS, the different types of GRMS vehicles, why do railroads and the FRA test with GRMS. We're also going to talk about the GRMS measurement parameters, how we review onboard exceptions, and how to correlate the strip charts and data to exceptions in track. And then what is the method of locating and verifying these exceptions, and what are the track specific conditions that cause GRMS exceptions? GRMS is something that Holland got into about 25 to 30 years ago by building track inspection equipment with GRMS that led to our successful track testing business today. Holland for years had a proprietary load axle design specific to GRMS testing. Looking at the definition by ARIMA, GRMS is the lateral restraint measurement system designed to perform continuous gauge restraint measurements using mechanical wheels to measure the unloaded and loaded gauge to applied test loads using GRM conditions. Nominal vertical test loads are controlled. Lateral test loads are produced by a nominal constant pressure hydraulic system acting through an axle wheel set. Again, that's the ARIMA definition. A gauge restraint measurement system is simply the best performance-based method to measure reserve gauge strength under train loading conditions. This slide reviews a couple of GRMS vehicle types. The first one being the self-propelled FRA DOTX 218, which has a deployable split axle. There are other GRMS types of vehicles that are usually converted passenger cars and pulled through with a train consist. The Holland TrackStar is pictured to the right, and the star part of the name refers to our strength testing analysis and recording, part of what we do. Holland has the largest contracting testing fleet of GRMS equipment in North America that performs geometry-based GRMS testing for more than 125 different railroads and transits annually. TrackStar also utilizes a split axle design. The most significant difference in our fleet is the mobility to travel on the road and rail versus being limited to just rail-bound travel. Another significant advantage of the Holland design is our ability to test all track conditions and structures, including the critical parts of the switch and in high-speed turnouts. So why GRMS testing? Well, it's really simple. We want to improve track safety. We want to provide exception reporting of weak track locations as identified by the system for railroads. As a performance-based measurement, it is the best indication of reserve gauge strength in track. This is also an objective measurement data set that is utilized for supporting spot tie maintenance and major tie program work. Utilizing this data will also allow for the railroad to prioritize the work being a supplement to validate any visual inspection tests that were performed in the field. It can assist the railroad in considering upgrading the class of track being operated, And this is also an alternative inspection to the FRA 213.110 and can be combined with both geometry and rail wear information. The basic GRMS procedures all revolves around load severity as defined by the FRA in Track Safety Standards Part 213. What you're looking to understand is the relationship between the lateral and vertical forces applied. The L/V ratio means the lateral force divided by the vertical force, and this must be greater than a 0.5 ratio. If the L/V is less than a 0.5 ratio, it will not develop the required load severity under normal loading scenarios. Additionally, the L/V must also be less than 1.25, as any L/V greater than 1.25 increases the probability of wheel climb in the derailment of the load axle. Down below, you will see what the actual calculation is for load severity in kips. This is equal to the lateral applied force minus all the vertical applied force times the coefficient of friction, which is approximately 0.4. This next slide, we look at the loading examples. So I have chosen the FRA DOTX 218 car, as well as the Holland Trackstar to give a comparison to understanding GRMS. The heavier rail-bound car is going to put down a vertical load pinning the rail of about 18,000 pounds of vertical force, and then applying a lateral load of about 14,000 pounds outward, which yields an L/V of about 0.78 when considering GRMS measurements for defecting. The Holland Trackstar is not weighed as heavily and utilizes a 14,000 pound vertical force with a 9,000 pound lateral load, and provides a kip force for load severity of about 3,400 kips. This slide is probably the most valuable slide here in the deck on this presentation for outlining typical GRMS loading and for everyone to understand the GRMS loading requirements per FRA 213.110, Part C, referring to 1B and C respectively in the manual. You'll see this graph that takes the applied vertical forces over the applied lateral forces, looking at the L/V ratio, where you can see that the yellow lines represent the low and the high end of L/V. And what you'll also notice is the green line represents the median L/V, which ideally is 0.8. Also on the graph are the two circles that represent what typical high rail loading is, which is generally from our Trackstar. And then you will also see where the typical rail-bound loading car is, which you're going to see from FRA DOTX 218 vehicle. The highlighted section in red is basically where you want to be for ideal L/V and what we would call the sweet spot for GRMS loading. Holland's Trackstar, we are at the minimal lower end of where you want to see to simulate what would be expected from a loaded train or locomotive traversing the track. You need a minimum vertical force of at least 10,000 pounds per FRA, which is why the red highlighted section flattens at the bottom on the lower part of the chart. The two diagonal lines increasing as the force increases the vertical load and applied lateral force respectively. This is the goal of GRMS engineering, and when you are looking at things from a dynamic state versus a static state with regards to geometry measurement. Now that we've given a little background on what GRMS is, you know what you're looking for, and from a loading perspective, why it's important, along with some of the basic engineering theory behind it. Now let's look at GRMS parameters and what exactly are we measuring. So the first two measurement types are unloaded track gauge and loaded track gauge. So the unloaded track gauge measurement for our Trackstar is done out in front of the truck, ahead of the load axle wheel. And then there is the loaded track gauge measurement that we get right at the load axle wheel itself. There are also other measurements. These are calculated parameters that we look at within our geometry and GRMS testing results. Those are PLG 24, which is a projected loaded gauge based on the assumption of a 24,000 pounds of lateral loading. And the other two calculated parameters are similar, which are GWR and GWP. GWR is the gauge widening ratio, And TrackStar utilizes GWP, which is a gauge widening projection. Now let's take a look at the measurement GRMS parameters and what are their specific definitions. So UTG, or unloaded track gauge, is a measurement of gauge under neutral loading condition. Measurements must be made no closer than 10 feet from any lateral or vertical application, and the UTG measurement is to be taken ahead of the load axle application. Loaded gauge is a measurement of gauge under a specified vertical and lateral gauge widening load conditions. Then we have projected loaded gauge 24, or PLG 24, which is an extrapolated value for the loaded gauge under 24,000 pounds of lateral load and a 33,000 pound vertical load. A common railroad standard formula below is PLG 24 equals the UTG plus A times the loaded gauge minus the unloaded gauge, where A is a factor derived from a ratio of extrapolated and applied loads. Gauge widening ratio, or GWR, is the measurement difference between loaded and unloaded gauge measurements linearly normalized to 16,000 pounds of applied lateral load. In GWR, this equals the loaded gauge minus the unloaded gauge divided by the lateral load times 16,000, where L is the lateral force. And then lastly, gauge widening projection, which is an alternative to GWR. This is where we measure the difference between the loaded and unloaded gauge measurements normalized for different loading configurations. A common railroad standard formula for this below is GWP equals the loaded gauge minus the unloaded gauge times A, where again, A is a factor derived from a ratio of extrapolated and applied loads. In this slide, we take a look at the chart that covers the GRMS threshold standards. So you'll notice that you have parameters in blue, and then you have red or urgent first level defects, followed by your yellow or priority second level defects and what their corresponding track deviation limits are. So the important one to look at here is really your loaded gauge measurement, second one down from the top. You have an urgent defect threshold of 1.5 inches, and then your priority level defect is set at 1.25 inches. Both of these being greater deviations from our original track standard of 56.5 inches for gauge measurement. The fact that the exception thresholds will change or be reduced based on track class and speed of track, of course. These next few slides will go rather quick, but what I've included is a sample GRMS exception report. This is pretty standard for what we give our typical customers, and you can see there's a header at the top of the page where we identify defects by number, looking at the worst location and then measuring back based on the length of the defect. So if you consider defect number 9, it identifies the milepost 224.16, or where the parameter of 866 feet past the milepost sign on track main 0. We have a red tag defect for GWP of 1.3 inches with the length of 12 feet. It is identified as class track 1, so this is an out of surface defect by the customer's threshold settings. We also provide a benchmark of CR, which is the curve, and it's about 210 feet from the curve and talks about what you're looking for as far as gauge wise, along with GPS coordinates for additional information to find the defect. This next slide shows a sample GRMS strip chart, and what we are looking at here is where you can see you have a GWP exception, and then you also have a second one, which is a GWP exception along with a loaded gauge. You may not always have a loaded gauge defect, and you can still have GWP or a weak spot in track identified. This slide is another sample strip chart, and what we are looking at here on the top line is both related to loaded gauge and unloaded gauge channels. The second channel is the curvature and cross level comparison, and at the bottom we are looking at GWP and PLG 24 channel. On the GWP, you can see that the yellow thresholds highlighted in yellow, and the red thresholds are where things exceeded as weaker areas of track for a level 1 exception. And then on the PLG 24, you can see where you didn't hit any of the level 1 exceptions, but where you do have priority exceptions in the same area. It's because of the more stringent and easier ability to identify the GWP that we utilize this with our TrackStar track testing. Since this is a weak spot in track, you'll see that the last channel is a tie plane channel. We'll recommend the number of ties to be changed out to correct the weak areas of track. Now that we have the strip chart reporting and understanding the defects, we create a work order to go out in the field. And how do we validate looking for where these weak spots can occur in track and where their corresponding GPS locations are? You can see from the pictures, the first one we identified is a weak area of track with missing loose or broken spikes and fasteners. And in the second picture, you can see the railroad worker using a PTLF, which is our portable track loading fixture, to load the track, which is no more than a little hand pump that goes out about 4,000 kips, which is actually greater than what our TrackStar lateral loading is at the 34,000 pounds of kip force when testing the rail. Next, the railroad worker will read the level board to measure where the gauge of the track is to mark the location of concern for remedial action. So now that we've determined it's a GRMS defect, and what we do for the total widening gauge at that load is we want to measure that it exceeds 5/8 of an inch when increasing the applied force from 0 to 4,000 pounds utilizing the PTLF. Widening in excess of 5/8 of an inch shall constitute a deviation from the first level defect thresholds. 5/8 of an inch of PTLF delta is approximately the same as GWR or GWP of 1 inch. And 1/2 an inch on the PTLF of delta is approximately the same as GWR and GWP of 3/4 of an inch. So finally, let's talk about track conditions causing GRMS exceptions. You're going to have loose or missing or broken spikes or elastic fasteners, worn, missing, or broken tie plates, pads, or shoulders. You'll get a cluster of weak, decayed, deteriorated, abraded, spike killed, plate cut, crushed, or missing ties. You get hanging or center bound ties, loose bolts, or worn joint bars, which have differential plate cutting. Additionally, I've included a picture of rail cant, which is what we utilize for evaluating concrete ties per FRA 213.234. This is one of the tests that is critical for most railroads that Holland performs annually. Here I've included pictures of track gauge conditions that specifically are with fastening on wood ties that cause GRMS exceptions. Please note the picture here on the bottom right-hand corner. As you can see, this is a high-speed turnout with unseeable broken lag screws. This is probably one of the best reasons for GRMS testing and is specific to Holland TrackStar for measuring track strength for high-speed turnouts. The reserve grade strength in an area like this will most likely result in greater than a 2-class drop in speed, where boots on the ground, you'll probably find a majority of broken lag screws about 3/4 of the way down into each tie that spans anywhere from 12 to 20 ties. We continue with examples of gauge strength conditions and track, where you can look at these are all concrete ties. In the first picture, you'll see that there are no elastic pads below the rail, showing clear rail seat abrasion and deterioration. You can see in the second picture, the center bound broken concrete tie. And the picture all the way to the right, you'll see where the fasteners are twisted and shifting. In the last picture on the bottom, you'll notice that this is where we are failing, and the concrete tie is cracked and rubber insulators are being pushed out from underneath the rail. Holland provides specific GRMS testing for the FRA 213.234 automated inspection of track that's constructed with concrete cross ties as a specific need for a majority of its customers. In conclusion, the recap of why GRMS is important. One thing is we want to improve track safety, and we want to provide exception reporting and weak locations in track. This is a benefit over just machine vision systems only because we have the ability to measure in snowbound areas mechanically as well as optically. This is also performance-based measurement of reserve gauge strength. And as an objective measurement data, it supports spot tie maintenance and major tie replacement programs. We can prioritize the replacement of our tie program work, supplement and validate visual tie inspections, and assist with considering any upgrading of track class speed. This is also FRA 213, an alternative to the 213.109 and 213.127 safety standards for testing, and can also be combined with geometry and whale wear information. Thank you for your time and attention today. Holland appreciates the opportunity to discuss GRMS and its application and how it plays a critical role in evaluating fastening systems, as well as the strength of track and its unique ability to identify weak spots in track both through visual and mechanical measurement.